Good evening, everyone. It's a pleasure to be back here. Thank you all for coming tonight, and welcome everyone online. This is a special day for me because it's the official publication day for my new book, The Joy of Science. So, very excited. It's also exciting for me because it's something of a departure for me from my previous popular science writing. It's a lot easier to write about stuff that I feel I know more about than my audience, the readership. So if I'm talking about quantum mechanics, I feel on safer ground, or relativity theory, or whatever. This book is really, I'm no more expert in sort of getting across some of this knowledge, imparting this wisdom than I guess many of you are. I sort of feel I've reached that stage in my career, that stage in my life. You know, I turn 60 later this year. I know I look not a day over 35. Thank you, madam. So we practice this as a joke. So rather than giving you clever stuff, I'm sort of trying to impart wisdom. I suspect, given the RI audience, knowing what you all like, I suspect I am sort of preaching to the converted. But what I want to do, and what I try to do in this book is not only just to get across my passion about science, why I'm still in love with the subject that I've spent my life, my career working in and thinking about, but also getting across how we do science, what the scientific method actually is, and how it actually might be beneficial for more people to adopt the very best of the scientific method. Now, first of all, I want to get across what science is. Now, science isn't a collection of facts about the world. You might think that's what science is. It's not. A collection of facts about the world. And that's called knowledge, right? And science is the way, or one way, we can get that knowledge. It's a process, a way of learning about the world. Now, there are many ways that we can gain knowledge, whether it's through art and literature, or poetry, or contemplation, or theology, or discussing it with other people who know more about the world than us. But for me, particularly when it comes to understanding the natural world, our universe, our place in the universe, then science has this big advantage over other ways of gaining knowledge, because it relies on what we call the scientific method. Now, why is it we should be thinking more scientifically? This is what I want to persuade you of in this talk. First of all, and this is something we've really come to appreciate over the past 2 years during this pandemic, is the importance of having a more scientifically literate society. It's empowering to understand a little bit more about our world and how it works. It doesn't mean we all need to be experts, but it means we have to understand we don't all need to be climatologists to know that recycling is a good thing, right? So understanding a little bit about how science works gives us confidence in understanding why maybe we should wear masks, or why we should be getting vaccinated, or why we should make sure we're in ventilated rooms. This is a large lecture theatre, so I think we're all safe here. So it is empowering to know a little bit more about science. But it's also empowering because it enriches our lives. Knowing more about how the world works is enlightening. Richard Feynman had this wonderful quote, maybe you're familiar with it. He said, "Poets say science takes away from the beauty of stars, mere globs of gas atoms. Nothing is mere. I too see the stars on a desert night and feel them, but do I see less or more? What is the pattern or the meaning or the why? It does not do harm to the mystery to know a little more about it." Unlocking nature's secrets is inspirational. It doesn't detract from the magic of our world. It doesn't remove mysteries and make the world cold and hard and rational. It adds to our understanding. It used to be that we relied on superstition. We didn't understand how things worked, and we came up with all sorts of reasons for explaining the spread of disease, explaining natural phenomena. Science has allowed us to appreciate and understand more deeply why the world is the way it is. The rainbow is a really nice example, and I know there are a number of authors who've used the metaphor of the rainbow to express why a scientific understanding is enlightening, empowering, and gives us more. I mean, certainly Richard Dawkins has a book title, Unweaving the Rainbow. People like Carl Sagan have talked about it. The poet Keats criticized Isaac Newton. He said Newton had destroyed all the poetry of the rainbow, reducing it to its prismatic colors. But of course, when you look at a rainbow and enjoy its beauty, understanding a little bit more about how a rainbow is formed only adds to that awe-inspiring image. Now, I'm not going to go through how light rays go through refraction, total internal reflection, and refraction back again. But the idea that there are billions of raindrops, sunlight passes through the raindrops and bounces back, it breaks up into all the colors of the rainbow. Every drop sends different colored light in different angles. So where you're standing, what your eye receives is light from a billion raindrops, each one of them sending you a different color. A person standing next to you doesn't see the same raindrop as you, doesn't see the same rainbow, as you, because the light entering their eyes comes from different drops in the air. A rainbow isn't actually a semicircle. It's actually a circle. If you were to stand on top of a mountain with the right angles, you'd be able to see the rainbow is a full circle. So a deeper understanding like that doesn't mean you look at a rainbow and think, it's just total internal reflection and refraction and it's boring and rational. No, it adds to that beauty. The third method for why we should all be trying to think scientifically is the fact that science relies on this thing called the scientific method. It helps us think more clearly. And in a sense, that's mainly what this book is about. What is the scientific method? What is so good about it? Why might it be useful for us all to adopt it more in our daily lives? Now, there's lots of ways of doing science, and there are many different types of scientists. An astronomer or a cosmologist might gaze up at the heavens to try and understand the structure, the nature of the universe. Medic or clinician might be working on a clinical trial to work out the efficacy of a new vaccine or a drug. The chemist works in the lab, mixing materials, understanding the structure of matter. The climatologist writes computer programs to try to predict how the Earth's climate will behave in the future. And then you have the Albert Einsteins writing algebraic equations on blackboards. These are all science. They're all doing science. So what is it that they have in common? What is it that they do that allows us to sort of differentiate something that is science from something that isn't science? Well, let's go through some of the things we might imagine science, doing science relies on. For example, coming up with a hypothesis, coming up with a theory that makes predictions, and you have to test it. You have to test that hypothesis by doing an experiment or going and making an observation and gathering data. But a historian does that. A historian comes up with a hypothesis about something that took place in the past. They then need to find evidence to support that hypothesis. Does that mean history is part of science? No, they're two very different disciplines, but they use that same approach of testing your hypothesis. We often say that to be a scientist, you have to be curious about the world. Well, that's true. But a conspiracy theorist is curious. In fact, a conspiracy theorist will say, I'm doing science. I'm being curious, I'm being critical, I'm testing an idea, I'm looking for evidence, I'm trying to understand something about the world. Is a conspiracy theory a scientific theory? Well, no. The difference is, and I will come to this later on, a scientist will change their minds in the light of new evidence. Ask a conspiracy theorist, what would it take to persuade you that you are wrong? They would have to say nothing. That's the whole reason. That a conspiracy theorist is so fixed on their view, it doesn't matter what evidence you provide for them, it's not going to persuade them or to change their minds. What about making predictions? Well, astrological charts make predictions. What if you read your star chart one day and it says that tomorrow you're going to get some good news at work? And the next day, your boss offers you promotion. Well, the star chart made a prediction that turned out to be correct. Is astrology then part of science? No, that was a coincidence. Luck. There was no scientific, rational explanation for, well, there isn't, to explain how distant stars, whose gravity is far too weak to have any bearing on anything on Earth, that will govern the human affairs on a daily basis, depending on when you were born. It's nonsense. So, astrology isn't a science. The flip side is very often people are so blinded by the power of science that they are too willing to believe something is scientific, even when the evidence for it is very flimsy. And we see this a lot, whether it's to sell yogurts or face cream. You add a chemical word in there, suddenly, that's scientific. It must be true. It must be correct. So we have to be wary, because not all science is good science. And we've certainly seen that during the pandemic, where people are so convinced about a particular aspect, something to do with whether it's the vaccines or whether it's to do with social behavior, that they're following what they believe is sensible scientific advice when it's not. The problem is, how do we differentiate? Who do we believe? Who do we trust? How do we know when the internet is full of so much information, we're bombarded with information all the time, how do we know what is true and what isn't? That's difficult. But adopting the scientific method can help us do this. So here are a few lessons from the scientific method. I will go through them. There's a chapter in each book. I sort of hesitate to call them lessons in the book, because I don't want it to sound as though I'm being patronizing or just being a bit arrogant in the way I'm imparting this knowledge. But they are, I guess, lessons that teach me how to do science. Something's either true or it isn't. Now, how many times have you gotten into an argument where you've stated something quite clearly that you think is a perfectly solid fact, only to hear the response being, well, that's just your point of view, or, well, that's one way of looking at it? It does seem increasingly, particularly amplified by the internet and social media, that there are many versions of the truth, or the truth is whatever we want it to be. We create our own truth. Now, something like cultural relativism is in its pure form, it's a good thing. Cultural relativism simply means being respectful of other points of view, other cultures, other ideas and beliefs. But that shouldn't infect this notion of truth. We don't all create our own truths. Now, in science, particularly in the exact, the natural sciences, like my field of physics, it's much easier to say what is true, what isn't. It is true that when I drop a ball from a height of 5 meters, it will hit the ground after 1 second. Not half a second, not 2 seconds, 1 second. Give or take a tiny fraction, but that's about right. And there's a simple formula that it was given to us by Galileo hundreds of years ago. That's an absolute fact about our world, about the nature of gravity, well, in this case, Earth's gravity. It would take longer to fall from 5 meters on the moon, for example. It's rather different when we talk about something being true or not true when it comes to the complex, messy nature of human affairs. Moral truths, for example. Well, here are 4 examples of moral truths which, on first reading, you might think they are incontestable truths, that they're not really up for debate. Is there such a thing as an absolute moral truth? Showing kindness and compassion is a good thing. Murder is wrong. Human suffering is bad. Actions more likely to bring harm than benefit are bad. There should be no debate about that. But even truths like this, which seem straightforward, need to be put into context. Showing kindness and compassion is a good thing. Well, that's sort of a bit of a tautology. You might as well say being good is a good thing. It sort of doesn't really tell you anything. Murder is wrong. Well, okay, how many people might be thinking if one of Putin's inner circle decided to take him out, wouldn't the world be a safer place? I mean, the usual example is Adolf Hitler before the war, before the Holocaust. But, if you were saving thousands or millions of lives, how do you judge whether taking one life is wrong? Human suffering is bad. Guilt and grief are a form of suffering. Are they bad? No, I don't think, grief is bad. Grief is part of the human condition. It's something we should go through. It's right. So not all suffering is bad. Actions more likely to bring harm than benefit are bad. Well, it depends who for. An action might bring benefit to someone but harm to someone else. How do you judge which wins? So even these simple truths that we think, well, they're straightforward, you put them into context and you realize, yeah, there needs to be some background to them before we can judge. But I'm going to give you some absolute truths about the world that I don't believe are contestable. These are, they're either true or false. You may not agree with all of them, but, if you don't, outside in the alleyway after the lecture. So I'm calling them facts. Now, and also, you see, scientists should never be, and I'll say this a bit later on, scientists should never be absolutely certain in their pronouncements or in their description about the world. There always has to be room for doubt, always has to be room for uncertainty in order for us to change our minds. Nevertheless, I'm still calling these facts because, as far as I'm concerned, 99.9999% confidence means it's a fact. Humans have walked on the moon. True. The Earth is flat. Not true. Life on Earth evolved through a process of natural selection. True. The world was created about 6,000 years ago. Not true. By the way, Lord Rutherford gave a talk in this very lecture theatre about the age of the Earth. And another great 19th century scientist, Lord Kelvin, was in the audience. And Lord Kelvin had decided the Earth wasn't he wasn't talking about 6,000 years, but he didn't know it was going to be billions of years old. So it's nice talking about something like this where Ernest Rutherford stood. But no, it's not true. The Earth was created 6,000 years ago. Don't care who argues with me. The Earth's climate is changing mainly due to humans' action. That's true. I mean, 10, 20 years ago, people might have said, well, we don't know for sure. It might just be a natural cycle of things. The overwhelming evidence now means that is no longer really up for debate. Nothing travels through space faster than light in a vacuum. Sorry, Star Trek and dilithium crystals, but this is true. That's the maximum speed in our universe, 300 million meters per second. Give or take, there are roughly 7 billion atoms in the human body. I said give or take because I didn't count them myself, but science is well enough understood that I can give a number to the number of atoms in the average human body. And finally, 5G masks contribute to the spread of viruses. Not true. Now, you may feel slightly uncomfortable about one or more of these points. The reason why I'm so bullish about them is because if any one of them were wrong, that I was wrong about any one of them, then we would have to pull down and dismantle the whole edifice of modern science. Because facts, but many of those that are sort of scientific facts have been built up over centuries of our understanding of how the world works. So if you would argue against one of these things, you would have to come up with a theory, a hypothesis that explains everything else, the thousands of other facts that science that has given us these facts has also explained so successfully. We can't just come up with our own truths when it suits. The second lesson, not everything is as simple as you think. Now, you may have heard of Occam's razor, the idea that the simplest answer is probably the correct one. Why complicate things when you don't need to? Let's have it nice and simple. Don't blind me with all the details. And increasingly, we live in a society where that is ringing true. We live in a world of memes and tweets where all nuance is lost. Everything's either black or white, one extreme or the other. There's no gray in between. Everything's, very straightforward. Now, of course, that's more. We see it more often in hard, solid science like physics or chemistry or astronomy. You might argue that everyday affairs shouldn't be. Our human lives and the human brain and society is much more complicated than that. It's not always so straightforward. We have seen this push, a trend towards simplifying arguments about whether it's ethical or political ideologies, where all subtlety or complexity is ignored. Everything is reduced down to its simplest, lowest common denominator. But not everything is black or white. Not everything is as simple as we would like it to be. Sometimes we have to put in a bit of effort to understand a subject. We see this online, when newspapers write about the culture wars or wokeism. I mean, that's mostly because they just want to pick a fight where there isn't one. But there are debates, important debates that are taking place, particularly across social media, where you're not allowed anymore to say, you're right, you have a point, but you also have a point. There's no middle ground very often. You're with me or you're against me. If you're not 100% with me, you are my enemy. And that's this trend towards simplifying, that there is people are no longer motivated to try and understand subtleties of arguments. Partly because we're bombarded with information all the time. And that's our way of filtering. That's our way of deciding what side of the fence we want to be. But sometimes we've got to put in the effort. Okay, next one. Just because you don't understand something doesn't mean you can't if you try. I'm not suggesting if I give a lecture on quantum mechanics that I expect everyone to be an expert in quantum mechanics. We don't need to know the details. My smartphone is full of quantum mechanics, right? The physics, the engineering, technology goes into a smartphone is incredible, is mind-boggling. But no one person knows everything about how a smartphone works. It's too complicated. But we can know a little. In the same way that we don't all have to be experts in plumbing, because there are experts who can do that better than us. When my plumber came round a few weeks ago, I had a problem with my boiler, and I said there's an error came up, F61, I think it was, and he saw it, he said, yep, I know what that is, the circuit board needs changing, I've seen hundreds of these, this error coming up, and I know that's what it needs to do. I didn't call him up and say, don't bother coming round, I've had a look on YouTube, I can fix it myself. No. I know that he's the expert in plumbing. He knows how to fix it. In the same way that I wouldn't profess to be a concert pianist or to be able to run the 100 meters in the Olympics. There are people who are better at certain things than others. But it doesn't mean we can't put some effort in just to understand the basics. I mentioned this at the start. We don't all have to be experts in climatology or environmental science to understand some aspects of sustainability. Or how to recycle our rubbish. We know that that's a good thing. We don't have to understand the details of the science behind it. But we need to put in some effort. don't value opinion over evidence. Well, again, it's social media, this is what we see all the time. Very often, because debates and arguments on social media tend to be so polarized, very often the people who know most about a subject are also the people who know where their deficiencies lie. They know where the weaknesses might be in their argument. And so they tend to be less strident. They tend to pull back. It's the people who know less who tend to shout the loudest. But there's so much out there. When I say we're bombarded with information, we're bombarded with misinformation, disinformation, fake news. How do we know who to believe and who to trust? Many people living in Russia, for example, now, who hear and see only one side of a story. They are being fed a narrative that is not the narrative of the real world. Now we can argue about ideological differences of opinion and seeing the world from different perspectives. But over and above that, there is a truth about the way things are. We can't just make our world up. That's called solipsism. When Donald Trump's supporters refused to acknowledge the results of the last election in the US, they were creating a narrative. They were creating their own reality. We can't do that. So it's the difficulty here isn't just getting evidence, but it's knowing what evidence to trust and what evidence to believe. And that's sometimes not easy. How do you know when you see something online who's behind that bit of information? Who are their paymasters? What is their motivation? And it's difficult. Our lives are too busy. Time is too tight for us to be able to go around investigating every piece of evidence about a particular issue to find out whether we can trust it or believe it. There need to be mechanisms in place to help us out here. Recognize your own biases before judging those of others. Now, this is something that the scientific method teaches scientists. Not all scientists follow it as well as they should do. But that is how science should work. In science, you come up with a theory, a hypothesis, you put it to the test, you then check it. You try and knock it down, because if it's wrong, it'll be knocked down by someone else. So you should be prepared that you may be wrong. Try and step back and judge whether you've done anything wrong in your experiment or in your mathematical theory. And in everyday lives, we should be a bit more willing to examine our own biases. Now, that's not easy, and it's not comfortable. We all like what's called confirmation bias. We like to hear what we already agree with and believe in. I suspect, given, again, I'm speaking to a Royal Institution audience, that I'd like to think that you mostly agree with me. And so I'd like to think that I'm just confirming your pre-existing biases. So we're doing it here. It's become more. This has always been the case, and we should not be blaming the internet or social media for this. In the past, life was simpler. We read one particular newspaper. If you read the Daily Mirror or the Daily Telegraph or whatever, you had a particular ideological viewpoint, and you read the newspaper that amplified or reflected that view. Nowadays, we have access to all possible views and opinions, including those that we don't like to hear, and we tend to only want to listen to those we already agree with. If you have an argument with someone, you have your own biases, your own view. My point is that in science, we always say in science we can disagree without being disagreeable. That's how we progress in science. We try and listen to the other side. We try and think, well, okay, well, maybe I'm not right. We're not there just to win arguments and score points. That's not how science works. You wouldn't make progress in science if it was simply about winning arguments. Now, I know a lot of scientists do that, but they are not doing good science. So recognizing your own biases is a good thing to do before you start judging other people's views. Try and examine where you've got your opinions from. Related to this is probably the most important lesson here. Don't be afraid to change your mind and admit your mistakes. A few years ago, I made a documentary for the BBC called Gravity and Me. So I was talking about the nature of gravity according to Newton and Einstein, and why does the apple fall? I got into talking about relativity theory and talking about how a gravitational field slows time down. Quite literally, it slows time down. And so I started talking about different points on the Earth. So when you're at the North Pole or the South Pole, because the Earth is squashed, it's oblate in shape, the North Pole is closer to the center of the Earth than points on the equator. Being closer to the center of the Earth means you should feel stronger gravity, and therefore clocks would run slower. However, if you're on the equator, the Earth is all going around on its axis, and you're moving. And Einstein also says one of the lessons of relativity is that something that's moving also causes time to slow down. Obviously, not very much, and you have to get close to the speed of light to see it very dramatically. But I went into the program went into this detail about how the two effects, what's due to Einstein's general theory of relativity, that gravity slows time down at the North Pole means clocks run slower, but Einstein's special theory of relativity, which says that motion slows time down at the equator, their clocks there would run slower. So which one wins? And we'd finished filming, and the editing was done, and I was due, I think, a few days later to do the voiceover, the commentary for the program. And then my exec producer called me up one evening and said, I've been looking at some physics chat websites, which is always a dodgy thing to do. And he said, but I think we've got something wrong. And I think, I'm not quite sure about the balance of different clocks and rates and so on. So he got me panicking, so I sort of dug up textbooks and looked online. I emailed half a dozen of my colleagues who are experts on relativity theory and discussed it and realized that I'd made a mistake. It turns out, in fact, the correct explanation is all clocks at sea level, anywhere on Earth, tick at the same rate. That's how the Earth formed originally. It's spinning at that rate, and it's stretched out when it was still malleable to the oblate shape to make sure that every point on the surface is part of what's called a geoid, an equipotential surface. Basically, I didn't have to worry about which clock runs faster or slower. They all run at the same rate. So anyway, okay, well that's wrong. We can't do this. This program can't go out as it is. And we told the commissioning editor of the BBC, and the message we got was, well, we just reshoot stuff, and no one will be the wiser, and we'll delay transmission, because that was going to be like in a few weeks' time. And I said, no, actually, isn't this a wonderful opportunity to show that scientists are quite happy to admit they've made mistakes? So what would be really nice was for me in the film to say, unfortunately, at this point, things went a bit pear-shaped, because I realized I'd made a mistake. And then go on to explain. So, oof, Jim, I'm not quite sure that's a good idea. We're worried about your reputation as a professor of physics. No one will trust anything you say. Not understanding that is how science works. Scientists who don't admit mistakes, if we didn't admit our mistakes in science, we wouldn't make progress. We'd be stuck believing what the ancient Greeks believed. That's how we make progress. Admitting your mistake is actually empowering. And we did. I got my way, and I said that. And I was getting emails after in the program aired saying, "Oh, Jim, you're very brave to admit your mistake." No, we do that all the time. Wouldn't it be refreshing if politicians could admit their mistakes and say, "I was wrong. I thought this, but I now have more evidence, more data. I've spoken to people. I've thought about it. I've realized that economic path wasn't the right way to go, and we're going to do this." But you see, in politics, admitting your mistake is a weakness. Love her or hate her, Margaret Thatcher knew what she wanted. This lady is not for turning. Doesn't matter, right or wrong. It's not changing your mind that's seen as the strength. It's the opposite thing in science. Doubt is not a pleasant condition, but certainty is absurd. Or, being certain about something, never being able to admit that you might be wrong, is a ridiculous state to be in. That's why we say in science we have to be uncertain. Now, uncertainty doesn't mean we don't know. It means we know what we don't know. We know we put error bars on. We understand the limitations of our current understanding. And I think wider society have started to appreciate this. There's still, a lot of people will say, oh, you scientists at the start of the pandemic, you told us to wash our hands and sing happy birthday twice through and then we'd never catch the virus. Now you're telling us we've got to be in ventilated rooms and windows open. What happened to the hand washing? You know nothing. And we have to get across the idea that science progresses. We didn't know that much about how the virus was transmitted early on. We've learnt, we've gathered data and information, and we've changed our minds in the light of that new information. The final lesson is stand up for reality. And I just want to end by, this picture is a famous story, the allegory of the cave, down to the Greek philosopher Plato. The idea is you have these prisoners in this cave, they're chained to the ground, they can't see around them or behind them. All they can see, all their lives, I know it doesn't sound very realistic, but let's bear with me. All they can see are shadows on the walls of the cave in front of them. Those shadows are made by people holding shapes walking behind that wall. Those people might be talking to each other or singing and chanting, but because of the echoes around the cave, the prisoners think those sounds are emanating from the shadows themselves. So for them, the shadows are their entire reality. There isn't anything else. Now imagine one day one of those prisoners is released and he's let out of the cave and he goes out into the wide open air and realizes there's a much richer reality out there. He understands that shadows are simply light blocked from passing through solid objects. The world is three-dimensional, shapes are three-dimensional, not two-dimensional like the shadows. Now imagine if he goes back down to his friends and tells them about this new reality. Well, of course, they're not going to believe him. They think he's crazy. Because this is their entire reality. They can't imagine or conceive of something richer beyond it. Now, Hollywood there are examples of this. The Matrix film, for example. The fact that we're all living in a simulation and there's a real world outside it. Or The Truman Show with Jim Carrey. He's playing this part in this soap opera that everyone's watching. But for him, he thinks that's it. The real world is everything. There is a bigger reality out there. Now, it may be that the reality that we perceive or that released prisoner perceives isn't itself the ultimate reality of things, but it's more richer and closer to the truth of how things are than the shadows in the cave. Plato's point here was that enlightenment is always better than ignorance, and those chains are the chains of ignorance. Now, by ignorance, I mean not appreciating that there's a deeper reality. It's not meant to say that it's wrong to be ignorant, but that knowing more about the world, celebrating the fact that there's a reality out there that we try to understand. We may never understand it. We may never reach the ultimate truth of the universe and how and why things are. But science tries to get closer to that truth. And that's empowering. That's enlightening. That's something to be celebrated, not something to be cynical about, that somehow, the cold, hard rationalism is boring. We don't all have to behave like Mr. Spock. Knowing something about the world is something to be celebrated, not to be afraid of. And I will end there. So thank you all very much for your attention.